All right, we got 30 seconds to go. And I hate to say it, I didn't have enough time to finish grading the entire class. I still got, I think only a few left, but I didn't quite finish it. So it will take me another maybe day or so, just because the day is broken up into tiny little pieces these days. All right. All right. Well, we are about 30 seconds past 10:30. I'm gonna get started because it's going to be a pretty packed last lecture of this class. So what I'm doing right now is going over exam questions from last semester. And for those of you who know me, that means you're not going to see questions exactly like these. Probably similar, but I cannot even guarantee that. But anyway, these are actual questions from last semester as final exam questions. So we'll go over these, first. The first question has to do with counting, and by extension, it also has to do with probability. So we'll go ahead and read the question first because the question itself is a little bit complicated. So it's important to understand it first. So you're a high school history and math teacher. In order to make both subjects fun, you decide to make a game that involves both. You start with a pool of 6 US presidents and 2 famous people who were not US presidents. So from this list you can see how we have 6 presidents, and then we have 2 people who are famous but they are not presidents. And for the presidents, they are numbered. So the sequence, Richard Nixon, and then Gerald Ford, and then Jimmy Carter, that is when they became presidents in that particular order. But it may not be complete. In other words, there may be presidents in between that I do not list here. But with the ones that are mentioned, that's the order of those particular presidents. So what you do is from this pool, you generate a huge stack of cards. Each card has 5 names chosen from the pool. So when I say chosen from the pool, it is a pool in this case of 8 names. So out of 8 names, each card has 5 on it. Ordering is considered important because within a card, the presidents, the ordering of the presidents, is significant. So the first question is, how many cards did we actually generate? Be sure to explain the reasoning and how you derived the answer. Insert your answer right below this paragraph. Explain how you come up with this answer in terms of in terms introduced in the class, such as experiments, trials, outcomes, with or without replacement, order significance, and so on. So that means this is a clue, okay? This is a very strong clue of how I want you to come up with your answer, okay? How to explain your answer. In this case, now I'm just going to verbally say it, okay? If you want to jot down some notes, that's fine. If you want to just kind of record the time mark and then come back later on to jot down the actual notes, that's fine too, okay? So what we are doing is to look at all of these things here. Okay, each card has 5 names chosen from the pool. So that means we have 5 trials in an experiment because each card is representing one experiment, and each experiment has 5 trials. Where each trial is really just drawing one name from the pool. I did not make it very clear that a name cannot appear twice on the card, but that really is the case. So if you have any questions like this, during the exam, you probably want to ask me, using a direct message on Discord, and just ask me, okay, can we pick a name twice or more times within a card? And then the answer is no. Okay. So now what we know is there are 5 trials in one experiment. we know it is without replacement. Once a name is chosen, it cannot be chosen again. So a name can only appear on a card up to once. And also, ordering is significant because it is actually, written here in the question that ordering is considered important. Okay, so so you have to introduce all of these elements, because once you have introduced all of these descriptions, mapping what is in the question to very specific terms that we have talked about in class, then you can now say, oh, okay, so the problem is to count permutations, because permutation is ordering significant and then combination is ordering insignificant. So since ordering is significant in this case, we're counting permutations. We're counting the number of permutations of choosing 5 out of 8 because the pool has 8 in it. So now your answer, after explaining with all those terms, now you don't need to use full, complete sentences if you don't want to. That's perfectly okay. But you do have to point out, okay, how many trials are we talking about per experiment? What is one experiment? Okay, is ordering significant, and why do you come up with permutation to answer this question? So I'll just go ahead and use a text editor on the side to explain, to have a short version of the answer. But the full version of the answer is going to also include all the explanations. But I'm just going to give you the short version, in the text editor here. So for the first part, the answer is permutation or permut. Okay, that's the actual formula name in the spreadsheet. And we are starting with 8, out of which we choose 5. So permut 8, 5 is the correct answer. And I'm just going to double check to make sure that that is the order, that we are choosing 8 out of 5, and this is how we represent it. I need to go find a spreadsheet to test this. Okay, I can just create one. I'm just doing it on the side to test that. Okay, so permutation 8 choose 5. Yep, so 8 5, this is indeed correct. Now, do you need to give me the exact number? No, not really. Okay, so if you don't want to give me the exact number, it's okay. But since you're going to be using your computer, with access to Google Sheet or Microsoft Excel and so on, it's not that difficult to come up with the actual number. All right, but the question has more parts to it. So you send some of these cards to students and ask them to characterize the cards. So you're not sending every single card to every single student, you're only sending some of these cards. We will get to the characterization later. In other words, you're asking students to characterize each card so that you can score their characterization. The number of presidents on a card can range, in this case from 3 to 5, because we just randomly choose 5 names out of the 8. And out of the 8 names, we know that 2, up to 2, are not presidents. So when you look at each card that only has 5 names, it is entirely possible that we just chose 5 presidents out of the 6 in the pool. But it is also possible that we have chosen 2 of the non-presidents and then only have 3 presidents on a card. So let us consider the stack of cards, and we'll call that stack as 4, where it contains and only contains cards that have exactly 4 presidents. So we're looking at a subset of all the cards that we generate. We're only focusing on the cards that have exactly 4 presidents, and we call that stack as 4. Given any card, not just from the stack as 4, a student would evaluate in terms of 1, how many of the names are actually presidents, and 2, whether those names are in the correct order or not. So the answer or the characterization of a particular card has 2 components in it. The first component is how many of the names are presidents, and then 2, whether it is true or false that within the presidents on that card, are they in the right order. All right. So are there any questions about? Nope. Okay, I'm not seeing any questions. So we're moving on. You can think of a student's characterization as a two-tuple, where n is a number to indicate the number of presidents on a particular card, and then b is a boolean, whether the presidents are sorted in an quote-unquote increasing order based on terms. Um, the following is the logic to determine the score of a characterized card. So a student will send back, a card with the characterization, and this is the logic. It doesn't really show well because it was originally in a text format. So when I look at text but look at it as markdown, it doesn't render correctly. But it is a conditional statement. Let me see what I can do with this. I can always just use an editor to show you that. Just give me a second here to prepare that. Alright, so we got that. And I just need to increase the font size a little bit because I usually use a tiny little font for my stuff. Okay, there we go. Alright, so this is really the same material, just being displayed as regular text instead of being considered as markdown and then converted into HTML. So this is the algorithm to determine how what is the score of a particular card with the student's answer in it. It is nested. If the number of presidents in the card on the card is correct, then we consider whether they are in the correct order or not, whether the student correctly identify whether the presidents are in the order or not in the order. If both of these are correct, then there's a score of 1. But if anything is missing, it's going to be a score of 0. So that means a score of 0 applies to a card where the characterization counted the wrong number of presidents. It can also be 0 can also be applied to a characterization where the number of presidents is correct, but the ordering is misidentified. So if the ordering is actually correct and the student says false, or if the ordering is actually not in increasing order but the student says true, both of those cases we get a score of 0. Okay. So I have an example, okay, and I made it clear that you can skip the following example if you already know how the logic works. But if you're not quite sure how the logic works, here's an example. So the card would list these names in this specific order. We have Richard Nixon, Albert Einstein, Gerald Ford, Jimmy Carter, and Ronald Reagan. And you can see that we have one non-president here. Albert Einstein is not a president. And then with the presidents, they are in the correct order. So that means, if a student answers a two-tuple of 4 true, then it has a score of 1 because it correctly counts the number of presidents as well as identifying the order as in the increasing order, which it is. A 4 and then followed by a false as a two-tuple would get a score of 0 because even though the count is correct, the ordering is misidentified as not in increasing order. And then another characterization of any number other than 4 as the first value of the two-tuple would automatically get a score of 0 because it is miscounting the number of presidents. So the next one, is also just an example, but I'm not going to go through all the examples. So now we move on to this part here. Given the stack S4, which is only consisting of cards with exactly 4 presidents, evaluate with step-by-step explanation the following. Insert your answer, explanation, and derivation of expression after each paragraph. Alright, so there are several parts to this portion of the question. The first one is, what is the total number in stack S4? Okay, so in other words, how many cards are in stack 4? How many cards have exactly 4 presidents, 1 non-president in that particular stack? All right, so now we have the question is, how do we deal with this, right? Because the lotto example is not going to be very helpful because in lotto we're only counting combinations and not permutations. In this case, we are counting permutations, but in addition to permutation, we got this non-president who can be, you know, at any place out of the five. Okay, so let me just try to explain what I mean by that. Okay, so let's just say that A, B, C, D represent presidents, and then 0 represents the non-president. So now we have A, B, C, D, and then the non-president can be anywhere, right? It can be this, can be this. I'm not even changing the ordering within the precedence. I'm preserving the ordering within the precedent. I'm just changing the location of the non-precedent among the five. So we actually have, guess what? 5 variations. Okay, so given the same permutation of the 4 precedents, the location of the non-precedent would basically generate 5 variations. So now the question is now to say, first of all, how do we pick 4 precedents out of the original 6? Okay, so combine 6, 4 will give us the number of combinations of 4 out of 6 precedents. Okay, but ordering is not important in the combination, and that is intentional. Okay, so now let's look at this as variable x. Okay, this makes it a little bit easier to talk about the terms. So x is a good number to start with, but the first thing we need to do with x is we'll say this is y. Y is x times permut. Okay, 4, 4. In other words, of each combination of 4 precedents, we have basically the permut 4, 4, or basically it's just 4 factorial ways to reorder within those 4 precedents. Okay, and so we'll say this is the number of permutations to arrange 4 precedents on a card. Okay, so we are almost there. So now we got z. Z is going to be 5 times permut, 5 times y. So z is now counting the number of cards that have 4 precedents and 1 non-precedent. Okay, because there are 5 places where the non-precedent can go on that particular card. So the question is, can we generalize this? Okay, in other words, instead of using a 5 here, can we generalize this so that we are basically counting what if there are more than 1 non-precedents on the card? Okay, because then it seems to get a little bit more messy. But in that case, it becomes, out of the 5 positions, how many ways can we choose 2 of those positions to place the non-precedents? But of those 2, the ordering is important as well. So it becomes permut 5, and then followed by in this case a 1, which is let me think about this. I may not be doing this right. Nope, I think I'm doing this right. So permut 5, 1. This 1 is the number of non-precedents on a particular card, and since we are limiting to the stack S4, it is just 1. So z is the answer to this question. Okay, so z, if you expand the entire thing, is permut 5, 1, the 1 being the number of non-precedents, times y, but y is just combine 6, 4 times permut 44. Or if you want to, look at it as a more, in a more convenient way, this is just your permut 64. If you combine the combin and the permut, so those two can be combined into just this number here. Are there any questions? No questions. Okay. So I'm going to give you the exact number here. So we have permut 51 times permut 64, and that number turns out to be 1800. So there are 1800s in stack S4. All right. So that's the total number, and within that total number, the number of cards where an answer of 4 true means earns 1 point. We'll call this number B, and don't forget to explain and derive the answer. So the 1800 that we have derived here includes, these cards where an answer of 4 true would earn a point. In other words, now we want to count the number of cards where the ordering of the president is correct. Is 4. Excuse me. There are exactly 4 presidents, and that means it's coming from the S4 stack. But we also want to make sure that the ordering of the presidents is correct as well. So that means we are looking at, instead of doing a permut 64 here, which gives us all the different ways of ordering the presidents on the card, it'll be a combin 64. So now we say B is permut 51. It still has a permut 51 in here, because there's that place, that one single place in this case, where the non-president can go. So that one is still there. But the permut 64 becomes a combin 64, because there's only one right way of ordering the 4 presidents. The other ways of arranging, they're all incorrect. But we only want to look at the ones where the ordering of the presidents is correct. So I'm just going to go to my spreadsheet and calculate this. So permut 51 times combin 64 is 75. All right, there we go. And then the next one says, the number of cards where the answer of 4 false would earn 1 point. So that means, there are 4 precedents, but everything in the stack S4 has exactly 4 precedents. But in this case, we want the ordering of the precedents to be incorrect. So we call this, C, okay. So C is rather easy to calculate because it is just, what we call Z here. But this Z is really also named A in the question because I think I specified that one here. So I call this, A, which is also, Z in the notes here. So C is really easy because all it is just A minus B. Okay, because, when you're looking at a card with exactly 4 precedents on it, either it has the order right or it has the order wrong. So once we have counted that there are only 75 of them has the ordering being correct, then the rest of them would have the ordering being incorrect. So that's why C is just A minus B, which is 1800 minus 75 in this case. And that is, okay, I'm just doing the calculation on a spreadsheet on the side. And that turns out to be 1725. All right, so we are almost done here. All right, the number of cards where we just answered that, but that's C. So assume a student who does not study at all makes a semi-intelligent guess, meaning the following answers has an even distribution. Okay, so a student, is basically just, randomly guessing. Okay, we give the student a card with 4 precedents on it and 1 non-precedent, but the student doesn't know. The student only sees 5 names. So that means, the student knows that, well, there's a chance that there are only 3 precedents on it and the other 2 are non-precedents. There may be 4, It may be 5 presidents on it, and then the ordering can be correct or incorrect. So so a student would basically have even distribution of these 5 answers. And the question is, what is the average score when we assume that these answers or these characterization have equal chances? So that is the last part of the question, and we want to apply. We want to calculate the average when the student is only given a card or given cards from the S4 stack, but without telling the student that the card is coming from the S4 stack. So as far as the student is concerned, there's no actual indication that a card has exactly 4 presidents. The student only knows that there are 5 names on it. Okay, but we know that there are exactly 4 presidents, but we want to calculate the average score given that is the case. So that is the last part of the question. All right, so we want to now figure out, what are the chances, what each answer would score in this case. So we know a 3 true is going to score a 0. Okay, scores 0. We know a 3 false scores 0 too, because they got the number of presidents incorrect. And the same applies to 5 true and 5 false. Okay, 5 false. Okay, the only 2 answers that may be right, okay, is a 4 true and a 4 false. Now, between these two, now we actually have to figure out the probability of when it may be right and when it may be wrong. But we got that calculated already. That's why we had the calculations of A, B, and C. Okay. So 4 true would score 1, 75 times out of 1800 times, and it would score 0 the rest of the time. Okay, so that would be 1725 divided by 1800. And a 4 false would score a 1. That would be the majority because most of the cards have the presidents in the wrong order. And it would score a 1, 75, it will score a 0 75 times out of 1800. So that becomes the basis. So what we need to do is to really just kind of add up all the averages, and then just divide the whole thing by 6 in this case. So now we are adding 0 plus 0 plus, okay, there are 4 zeros here, and then we add up the average of these two. Okay, so the 0 we don't have to actually add because it doesn't really add anything to it, so it becomes really just 75 divided by 1800. And then the last one is going to be 1725 divided by 1800. And then you look at the summation of all of these and then divide that by the number of possible characterizations. So, and there are 6 of them, so you divide that by 6 and that becomes the answer. Now you can probably tell that these two numbers added is really just 1. Okay, I have to reselect the portion that I really want. So these two numbers just add up to 1. So that means we are looking at 1 divided by 6, and as a result the answer is just 1 over 6. So if someone were to just randomly guess, okay, the answer is just 1. The score would be 0.167 basically. The average score would be 0.167. Alright, so are there any questions about this one? This is the first question. It's a little bit long, it's a little bit complicated. No questions. Alright. I'm checking the text channel too, so we are not seeing anything here. Okay. So now let's move on to the second question. And I'm just going to use the text editor here for the second question too, because otherwise it's going to be potentially it's going to be rendered incorrectly. And by the way, you have I have pushed a zip file in today's text channel, and you can unzip it and find all of these same questions over there. So that's nice because you can actually annotate those. So the second question has to do with Dijkstra's algorithm, and I give you a trace. Okay, so let me just kind of fast forward to the trace. So this is the trace where the indentation is matching the nesting of the algorithm, and I'm indicating what is happening for the in the variables. So Q is a variable, V is a variable, and then the actual vertices are numbered, I think N0 to N8 in this case. So basically this is a full trace, and the question is asking, your answer is to figure out the original graph. G equals to VE. I'm reading this part of the question. And propose a distance function that generates the included trace when Dijkstra's algorithm is applied. In other words, I want you to use the trace to reverse engineer, okay, to reverse engineer the graph itself and also the distance function of all of the edges within the graph. So it's the reverse of what we do in class, because in class I give you the graph and then we work out the trace to get to the answer of E prime in this case. But in this particular question, it is exactly the opposite. I give you the trace, but you have to go backwards to figure out what the graph is going to look like and what are the distances between the edges. There are many ways to do this, such as plugging in numbers and trial and error. That would not be very effective, okay? But you can also use a systematic way to do this. So a more systematic way to do this is to figure out the relationships of edge and distances. As a hint, your first task should be reconstructing the edges first without considering the distances, and figure out set S, the set of all the destinations. Once you have this done, it may be a little bit easier to figure out how distances of edges relate to each other. Make use of the algorithm to explain how you figure things out. The final answer should include the set of vertices, the set of all edges in the original graph, the distance function d, which maps edges to real numbers, and the set of destinations s. If you find it more helpful, you can also include a hand-drawn picture in the document. You can insert your reasoning interleaved within the trace itself. And here's the trace. Alright. So how do we approach this problem? Okay. So the first thing you want to do is to say, Q is initialized to N8, N1, because that's the initial state of Q at the very beginning of the trace. That tells you one particular answer right away, doesn't it? Okay, so I'm going to use a pound sign here to separate what is in the trace and my explanation and what I figure out at this point. So what I do figure out at this point is the set S has exactly N8 and N1 in it, because that's how Q is initialized. It is initialized to be the set of all the destinations. So this is this part is rather easy, right? So all of these does not give me a whole lot of information, but this one gives me some information. Okay, so the fact that I am considering the distance of N3 and 8 means that there's an edge. Okay, that edge exists in E. So now I can say N3 and 8 is in the set of all edges. Wow, okay. So we know that N3 as a vertex, is only one edge away from the destination vertex of N8. That is rather helpful. Okay. And then there's a whole lot of question marks. Okay, the question marks basically goes like, Well, we know we are updating L of n3, but we don't know what it is, okay? Because there are many different possible answers to this question, and I want you to assign your own values, in this case. So we are not really, we don't exactly know what it is, okay? So we'll just say that L of n3 is now does not equal to infinity. It was infinity to begin with because that's how every L value is initialized, except for the L value of the destination vertices. This part here doesn't tell us much. This one doesn't tell us much. And in here, okay, because we are now considering another edge. So we also know that N7 and 8 is also in E, okay, which is really helpful. And we know that we're updating the L value of N7, but we don't know how we are updating it to at this point. So at this point, all we can tell is it is not infinity. And over here, we evaluate yet another edge. So we know that edge has to exist first. So that means N6 and 8 is also in the set E. And once again, we don't know the exact distance of that particular edge. So, but we just know that N6, L of N6 does not equal to infinity. So now we get back to the while loop. Okay, so at the while loop, this time we chose N1. That by itself doesn't give us a whole lot of information because we know N1 is part of the set. It's in the set of all the destination vertices. So this really doesn't tell us much. Okay, so we will just go like, not much information here. But this does tells us, some information. The fact that we are evaluating, L of n1 plus the distance of n5 n1 means that n5 n1 is an edge. It is in E. The value L value is not really that important. And now we look at this and go like, okay, we have just confirmed another edge, n0 n1. It's also in E. Alright, so now we have removed all of the destination vertices from Q. Now the fact that we are choosing N3 is really important because we always choose the most promising vertex in Q to be considered first. So this tells us something, right? It tells us that the L value of N3 is the least within what we have here. But that also means, because everything is only one edge away, so that means the edge N3, I think, to N8 has the least distance of all the known edges at this point. Okay, so if you're drawing a picture on the side, it's going to be very helpful because now you can say, okay, that particular edge has the least distance, and over here we can now say that we know that N7 N3 is in the set of E. Okay, and that's it. Okay, so we are basically reconstructing the graph as we go through all of this stuff here. I see a private message, but not from this class, so I'm going to ignore that. Alright, so the next one that we have chosen out of the set is N0. So what that tells me is the distance of N0 to, I think N0 goes to where? N0 goes to N1. So N0, N1 is the second least in the set of edges that we have explored so far. So basically, we are just using these methods to reconstruct the graph. So now we also know that N2, N0 is in the set of all the edges. And now we choose N6. So you have to be once you have a picture, it's really helpful because graphically, just visually, how the vertices are connected. It is important to understand that some of these vertices are now more than one edges away from the destination, so the L value does not represent the distance of an edge anymore. Um, but you still kind of need to follow through that step by step. But as I said, the first thing you might want to do is really just to reconstruct the graph itself. So now we know N2, N6 is in E. Okay. Yep. Okay, that makes sense. Um, and the fact that after the fact that this is true, this condition is true, means that L of N2 was updated here, but is updated again. Okay, so we know that the new path is found. Okay, so we can now say that there are at least two paths from N2 to destinations. So this is important because and also we know that the edge N2, N6 is leading to a shorter path to a destination. Okay, so that is also important. And now over here we see that there's an edge N3, N5. N3, N5 is in E. But once we evaluate that edge, we did not find a shorter path. So that means the newer path of N3 going through N5 to a destination is not shorter than what we have found so far. Okay, so that is also important. That tells us about ordering. And here we have a new edge. So this new edge is N7, N2 is in E, and that helps us find a shorter path for N7 to get to a destination. So we'll come back and reevaluate these things later on. And that's it. Okay, we have not evaluated any additional edges at this point. Let me hook up my tablet so that we can use a graphical way to look at this. All right. So it is really important to understand, as I'm hooking up things, I'm just going to talk a little bit. It's very important to understand the algorithms, because, I'm really just using the algorithms to figure out all of these things. And, also look at the trace and see how much information you can extract out of each line of the trace. Okay, now some of these are more important and some of these are not as important, but they are all important. I shouldn't say all of them are important, but some of those are very, very useful. Alright, so I got my tablet up and running, and we'll go back to the tablet screen here, reset this, and I think it's good to go. Yep, okay. Alright, so let's see how we can do this. I'm looking at this because I want to show you the trace itself as I construct the graph. So I'm just trying to figure out the best way to do this. Alright, so I think this might work. No. Okay, let me resize the browser and display. Okay, this is going to take a little bit of coordination here because I need to look at how much screen space is being captured and make sure that my own picture is not in the way. So it's in the way a little bit here, but I want to maximize the area where I can draw stuff. Okay, so at this point we know that, okay, so this is as far as I can go on the graph. So I'm drawing a line here so I know where I can stop. So we know N8 as a vertex and n1 is a vertex, those are the destinations. Okay, so we'll say these are our destinations. We know n3. Okay. Um, okay. Excuse me. All right. So we know n3. Uh-oh. Hmm. So we know n3 has an edge going to n8. We know n7 has an edge going to n8. And okay, I'm gonna turn off my webcam for a time here, just because it's not really that helpful at this point. So we also know that n6 has an edge going to n8. And then in the text editor, let me page down. And then n5 goes to n1. We also know that n0 goes to n1. And that's it. Okay. So that's what we can reconstruct up to in the trace up to this point or so. Okay. So now we choose n3 to expand next. Okay. So we know this edge. Okay. This particular edge here has the smallest cost amongst these other edges already explored. So we can kind of like we can say d of n3 n8 is less than the other edges. So I'm just gonna take a abbreviation here. It will be less than the distance of n7 n8, n6 n8, n5 n1, and n0 n1. Okay. So the distance of that particular edge is the smallest amongst these five. And then we see that there's an edge of n7, n3. So n7 connects to n3 like that. And it is a shorter path. Okay, so we know that n7, n3 plus n3, n8 is less than n7, n8. I'm using shorthands, so I'm not using the D and the whole notation. I'm just looking at a path this time. Okay, and all the distance of the edges. So that's what we got out of this part of the trace. And then in the next part, we find that there is an edge n2, n0. So n2 has not been introduced into the graph yet, so we have n2, n0 like that. And it also triggers an update because it got into the then branch of the conditional statement. So, which is not surprising because n2, would have a infinity value as its L value to begin with. So that doesn't really give us a whole lot of information. And this one does. Okay, n2, n6. So we know n2 also connects to n6. But n2, n6 triggers an update. So that means we know that n2, or the path n2, n6, n8, this path has a length that is less than the other path, which is n2, n0, n1. Okay. So once again, I'm using a shorthand. I'm looking at the length of the path, and so that three tuple is not really exactly a tuple. It is representing the length of a path. All right. So moving on. And then we look at n3, n5. Okay, so n3 has been introduced already, so there's an n3, n5, but it did not trigger an update. Okay, it did not get to the then portion of the conditional statement. So we know that n3, n5, n3, n5, n1 as a path has a length that is greater than what we have found already from n3, which is from n3 to n8 directly. Okay, so we are really just looking at the ordering of things right now, and then we also see n7 and n2. Okay, I think this is supposed to be n2. I probably just mistyped something on the keyboard and erased the n, or I did not type it in. So we have n7, n2. So n7 to n2, like that. And it did trigger an update. Okay, so we know that n7, n2 to n0 to n1, that path has a length that is shorter than the path that was original from n7 to n8. Okay, so n7, n8 as one single edge is quite costly because it is longer or has a distance that is greater than the length of the path from n7 to n2 to n0 to n1. Alright, so given this is what we can glean, out of the trace of the algorithm, this part is the graph itself, okay? But we still don't know the distance function of the edges, so the next thing we need to do is to work out, certain values for the distances so that it will work. So one thing we know is, so we have to use all of these comparisons to come up with, values that will make this graph work. Okay, so I'm just thinking here. So we know that n7, n8, has to be a pretty large value, because it is longer than this entire path. So out of these relations, we know this portion is greater than this portion, and so we have n2, n6, n8, and n6, n8 is just a single edge. Alright, so n3, n8 is the smallest of all of these edges, so we'll go ahead and give it a really small value. So let's say we start with a 1 for n3, n8, and then we look for other clues. So n8, n3, n8 is also less than n3, n5, n1. So we cannot put a 2 here because so let's say we start with a 5. I guess it's better to start with a 5. And then we say, so now we have to look at n5, n1 and see where it appears by itself. So it does appear by itself here. Oh, okay, never mind. I read my comparison operators backwards. But that's okay, we can keep that 5. So if that is 5, then n5, n1 is going to be more than 5. So the n3, n5, n1 would also be greater than 5. So we can try a 6 for n5, n1. So n5, n1, we can try a 6 here. And then we have n6, n8. Okay, n2, n6, n8 has to be less than just trying to think of a systematic way to work this out, because we have all of these ordering. So n7 and 8 is going to be a pretty big value. So n7 and 8. Okay, we'll give it a really large value here. Just so that it's the largest. And then we have to figure out the other ones step by step. So we got n7, n3, and 8 is less than n7 and 8. Okay, so we know n7 and 8, which is already a large value. So we want to be able to get through n3 to get to n8 and end up with a smaller value. That's not too hard. Okay, because n7 only has a few outgoing edges. So n7 would also go to n2, and we want to know how that looks like. So that is also going to be that's going to be less than n7 and 8, and that is eventually the shortest path that we found. Okay, so that means whatever value we put here cannot be so n7, n3, n8 is not going to be as short as n7, n2, and then n0 and then n1. So that is the shortest path from n7 to a destination. So let's see what value can we put here. Okay, I'm just going to put a 1 here and a 1 here and a 1 here. So now we have a length of 3. So we can, if I put a length of 1 over here, that would work so far. But I have all of the other constraints to also think about. So we have n2, n6, n8. n2, n6, n2, n6, and 8 has to be less than n2, n0, and 1. Okay. That doesn't make sense because n2, n6, n8. So this is actually going to be a even shorter path, but that was not explored first. Okay, so I might have taken my notes wrong here. So n2, n6 is the last one that we explored out of n2. Okay, I might need to rework this a little bit because I think the ordering of these sequencing, over here, I did not give a sequence here, so some of these comparisons, may be incorrect, or some of these confirmation of distances can be incorrect. So I'm going to come back to this one in just a little bit, or if I don't have enough time during the lecture, I will basically just attach another recording to this. But this is the way we kind of think about it, but I think I made a mistake somewhere within the confirmation of the ordering, and that's why it's not working out so far. Alright, so I'm gonna start with the next one, okay, which is the last question. So this is probably what you should be doing too in the actual exam. Now you have 2 hours in the final exam, not 80 minutes. So you have full 2 hours to work on your questions during the final. So you might want to time yourself, okay? Because if all the questions carry equal weight, then you want to time yourself and allow yourself a little bit less than 1/3 of the entire duration. So this way you have a little bit of time for the overhead, switching between questions and so on. If you are out of time for one particular question, you just kind of go like, okay, I'm gonna come back to this later, because you don't want to be stuck in one question and not be able to even take a look at another question, because it is possible the other question is actually easier. Okay, so you don't want to miss out the chance to answer an easier question. Then if you have time, then you can always go back to the earlier question where you were stuck. Alright, so I'm gonna pull the text window back all the way here so that we can read the entire question. So this one also has to do with counting, and this one, specifically, has to do with binomial distribution because there are only two things to choose from. Alright, so I'm going to read the question here. In a bag of marbles, we only have two colors, red and blue. The chances of getting a red marble is 0.1. If we randomly draw 10 marbles from the bag without putting down marbles back in the bag, what are the chances that 5 of the drawn marbles are red? Okay, so here's the first question. But wait, do not answer yet. So this problem is a little bit more tricky than it seems. The issue is the total initial number of marbles, what that number is. Okay, how many marbles do we start with in the bag? First, assume the bag is magical and you can draw as many marbles as you want and the chances of getting a red marble remains constant. It's always the same. Using the following space to explain how you get the probability, use the following space to explain how you get the probability. Terms that may be useful in this explanation includes, guess what? Experiments, trials, outcomes, with or without replacement, binomial distribution, event set, omega, and so on. Alright, so the only thing that we have just briefly touched on and not really a whole lot is the event set. So the event set is really the set a set of all the outcomes that we're interested in. In this case, getting a this is the event that we're interested in, that we want 5 of the drawn marbles to be red. And we are drawing 10 marbles. Okay, so we are drawing 10 marbles out of the bag, and we only want to count the outcomes where 5 of the 10 are red marbles. Okay, so let's use all of these terms to explain, to think about what we are processing here. So each experiment in this case is to draw 10 marbles. So that means there are 10 trials per experiment. The outcome of each trial is either red or blue because we are drawing marbles out of a bag where it has red and blue marbles. So the tricky part of this question is, should it be with or without replacement? Now, if this is a regular real life bag of marbles, then it is without replacement. Okay, once you draw a marble out, it would influence the probability of choosing a red versus a blue marble next because you have just taken one out of the bag. But the question did mention that this is a magical bag of marbles, okay, where the probability does not change. So if the probability does not change, that means we are dealing with replacement. Okay, so it is a bag, but you can kind of imagine that somebody is in the background, through a hole at the bottom of the bag, put back in a marble that you have drawn out. Okay, if you took a red marble out, then somebody is actually behind the scene putting a red marble back, so that the chances of getting a red marble remains to be 0.1 all the time. Okay, so if that is the case, okay, it is no longer a binomial distribution because let me see, it is a binomial distribution. I take it wrong, sorry. So in this case becomes a coin flipping problem because we're basically, if you think about a red marble as head and a blue marble as tail, we are basically flipping a heavily loaded coin where the chances of getting a head is just 0.1. So it does become a binomial distribution where our interest is looking at 5 heads and 5 tails out of 10 coin tosses. Okay, so given that is how we are recasting the problem. Okay, so I'm gonna use my tablet here to answer this question. So I will go back to the other one when I have time to do it. Probably I have to record a separate recording for that one because we may be out of time soon. So what we're doing here is we have 10 trials per experiment, and then the outcome of each trial is either a red or a blue. It is with replacement because the bag of marbles is magical, and it is a binomial distribution. Binomial distribution. Distribution. There we go. And our interest is to have 5 red and 5 blue marbles. So based on binomial distribution, it becomes 10 choose 5, and then the chances of getting a red marble to the power of 5, and then the chances of getting a blue marble to the power of 5. So that becomes the answer. But in order to get points, okay, you also have to basically answer all of these as well, because this is how I can understand that you know how to frame the problem to get to the answer. Alright, so moving on. Second, assume the bag has a smaller number of marbles. Small number being not infinite. Okay, it's no longer a magical bag of marbles. First of all, compute the minimum initial number of marbles in the bag so that it is possible to draw 5 red ones according to the ratio of red marbles to the total number of marbles is 0.1 to 1. Alright, so let me explain this part first. Okay, so we are basically saying the initial distribution or the ratio between the number of red marbles versus the total number of marbles is 0.1 to 1. So in other words, 1/10 of the marbles are red. Okay, that's what it's saying. So based on that ratio, we want to be able to draw 5 red marbles. So that means the minimum number of red marbles is 5. But since red marbles only make up 10% of all the marbles in the bag, that means we have 45 blue marbles in the bag. 5 red ones and then 45 blue ones. Okay? And the question is asking the minimum number of marbles, counting both red and blue ones. So that means the answer is just going to be 50. Okay, so the answer to the second part of this question is 50 because we are looking at 5 red marbles, which is what we need to have as a minimum, and then we divide it by its proportion in the bag, and that will give us 50 marbles altogether. Okay, and these are 5 red marbles, and then the 0.1 is the ratio of red marbles. So I'm identifying each part of the answer of how we got those specific numbers. Alright, so that part is done. And third, based on this finite initial number of marbles in the bag, so this time we know there are 5 red marbles and 45 blue marbles. Compute the chance of drawing exactly 5 red marbles out of 10 from the bag. Okay, so you might think, hey, we are doing the same thing. 5 red marbles out of 10, and then up here we also have 5 marbles out of 10. So do we just kind of repeat the answer to the first part of the question? The answer is no, okay, because this time the bag of marbles is no longer magical. So that means after you pick something out, it would influence the chances of what you're going to choose next. Okay, so once again we want to use all of these terms. Okay, experiments, trials, outcomes, with or without replacement, binomial distribution, event set, and omega. Okay, alright, so let's see what we're dealing with here. Once again we got 10 trials because we are choosing 10, we're picking 10 things out of the bag, and each time we pick one thing is one trial. The outcome of each trial is also really just red versus blue. Okay, red versus blue. There we go. Okay, and this time it is without replacement. Okay, and it is no longer a binomial distribution. Okay, this is not a binomial binomial distribution, because binomial distribution only works when it is a with replacement type of experiment, but now that it is a without replacement experiment, we can no longer, okay, say that it is a binomial distribution. So, what are we looking at? Okay, so this time it is helpful to look at um, the event set, and also to look at omega. Okay, because the probability is the cardinality of the event set over the cardinality of the all the possible outcomes. Alright, so let's go back to the question, and this time we look at this and go like, what is one outcome to look, how do we cast this problem? So that becomes the next question. Because if you choose one red marble, then you have only 4 marbles left that are red, but you still have 45 marbles that are blue. So the chances of getting a red marble, as in your second trial, is going to be different from the first one. It's going to be less than the first one. And I got a whole bunch of direct messages. Let me check those out first. And it's from my other class, and this one is also from my other class. Alright, I just got a whole bunch of messages from my other class because they got a homework assignment due today. So I'm gonna ignore those for now and go back to my current class where there are no questions whatsoever. Okay. Alright, so so the third part requires a little bit of thinking, okay? But we know that there are only a few ways that we look at this, right? Because if it's not a binomial distribution, then it is and it is without replacement, right? So experiments that are without replacement between the trials usually can be casted to a combination versus a permutation problem. Okay, so now we have to switch our minds to think in terms of combination versus permutation. Okay, so now the question is, well, between those two, what is the difference? The difference is, with permutation, ordering is important, and with combination, ordering is not important, right? Okay. In this case, the question is only asking, drawing exactly 5 red marbles out of 10. It didn't say anything about the interleaving between the red versus the blue marbles out of the 10. In other words, if you have red, red, blue, blue, red, 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 and then the rest blue, it's good. We count that. If you have red, 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 and then blue, 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 we'll count it too. So ordering is not important in this case, which is going to strongly suggest we should use combinations. So, when it comes to the answer, okay, you go like, okay, ordering is not important. So we are using combination. Or combination becomes an important concept in this question, in the answer. Okay, so now we have to think about what are we going to do with these combinations? Because combination and permutation too has to do with, this is how many we start with, and this is how many we are choosing from it. Okay, so from that perspective, we basically start with 5 red marbles, and we have 45 blue marbles. Okay, and we are interested in the case where you choose all 5 red marbles to be in the final collection, and you choose 5 of the 45 blue marbles in the final collection. Okay, so those are the number of ways we can pick these things. So so there are choose five ways to get the 5 red marbles. In other words, it only has a count of 1, which is fine, not a problem. And then we have 45 choose 5 ways to get the blue marbles into the final collection. Okay, so this number is giving you the total number of outcomes where ordering is not important, to have 5 out of 5 red marbles and 5 out of 45 blue marbles. So that is not a probability. Okay, this is basically the cardinality of the event. Okay, because the event that we're interested in is to end up with 5 red marbles and 5 blue marbles where ordering is not important. Now we need to look at omega. Okay, in other words, what is omega going to look like? Well, omega is going to look like so the important concept here is to look at each blue marble as a different marble. In other words, we have blue marble 1, blue marble 2, blue marble 3, and then all the way up to blue marble 45. Okay, so omega is basically just saying, oh, we got 50 marbles to begin with, and we're choosing 10 of them to be in a bag. That is our omega. In other words, omega is the set of all possible outcomes, and all the possible outcomes is merely just blindly reaching in to the bag and say, I'm just going to pick 10 marbles out of the bag. Okay, but then you look at the 10 marbles that you have chosen. Now you say, okay, what counts as part of the event and what does not count as part of the event. What counts as the event is the cases where you have 5 out of the 10 marbles chosen are red. If it is not, then you go like, nope, this doesn't belong to the event. So the cardinality of omega is 50 choose 10, and then the cardinality of the event is basically 45 choose 5. So the probability is now 45 choose 5. Now if you want to put a 5 here, 5 choose 5, that's fine, but that just boils down to 1. It doesn't really contribute anything to the calculation. But the denominator is 50 choose 10 because you have 50 marbles combined to choose from, and then you just want to pick 10 for each experiment. So this is the final answer. But to get to the final answer, you need to go through all of these steps in order to identify how to characterize this particular problem. So to give you an actual answer of the numerical value, let me just kind of go through this calculation so that we can actually look at how the answer to this part of the question is different from the earlier part. So after the calculation, on the side using a spreadsheet, this value turns out to be pretty small. Okay, it is 0.0001189 and so on. Okay, so that's a pretty minute probability, and we can look at the other one too. The one that we have written up there. So we'll go ahead and compute that one too. So it's combin 10.5 times I think it's just pow. Yep, it's 0.1 to the power of 5 times 0.9 to the power of 5. So that one is has a better chance. The chances is actually higher. It is 0.001488. So when you compare these two numbers, the magical bag of marbles would give you more than 10x the probability of ending up with 5 out of 10 marbles being red. And when you look at the realistic one where you only have 50 marbles to begin with, of which 5 are red and 45 are blue, the chances of getting all 5 of the blue excuse me, all 5 of the red marbles is actually very, very small. Okay, and that has to do with once you have chosen a red marble, the chances of getting another red marble is getting smaller. Okay, so that's kind of the intuitive way of looking at this. All right, so we are running out of time in today's lecture. As I said, I will work on the other problem and give you a better explanation of how to systematically do it. I think I did it. I did the systematic part correctly, but I wrote down the comparisons in the wrong order, and as a result, some of the constraints cannot be met. So I'm gonna work on that one and upload a new lecture, new recording for this class. All right, so here's our last lecture, and are there any questions about this class before I end today's lecture, which is going to be the last one? All right, cool. And I'll give you guys the survey, for the time of next Thursday. I might change the format too. I might allow a little bit more flexibility for the final exam. So I have to kind of work that out too. All right, you're more than welcome. Oh, for the lessons. Okay. All right. Cool. I'm going to stop the live stream at this point because I think I got some other questions I need to answer from my other class. So if you guys have any questions, go ahead and direct message me or use the text channel to message me. Other than that, we are pretty much done. I still owe you that recording of question number 2 of today's review, but other than that, we are pretty much done. All right. So I'll send you further information about the final exam, in terms of the format. It's going to be pretty close to exam 1 and exam 2, where it's open book, open notes, no collaboration during the exam. You can use tools like spreadsheets. You can use all the material that I have introduced in this class. Text channel will be turned off, but you can still direct message me to ask questions. So pretty much the same format. It is a little bit longer. You have a 2-hour period to answer the question, to answer the exam once it has started. That's about it. Alrighty, I'm gonna exit the screen sharing now, but I will still be online because I got a whole bunch of questions lined up to answer for my other class. Alright, bye and have a nice weekend if I don't talk to you again.